All right. Next is question number 11. This question 11 is an interesting problem. Interesting in the sense that for fluid, we use a Bernoulli's equation, but Bernoulli equation is valid under what circumstances? It is valid under circumstances that the density of the flow remains, liquid remains constant. Fluid should have a constant density, because if the density changes, then the conventional Bernoulli's equation will not hold. The Bernoulli itself comes from Euler's equation. Euler, you know, was a Swedish mathematician who actually derived this equation of flow from Newton's law, that is F equal to ma. If you consider all the forces, that is force of gravity, force of pressure, force of viscosity, force of turbulence, and then force of compressibility, all these forces together give you the net force. Okay. But if you are considering, let us say, you're dropping this compressibility force, then this whole equation in this particular form is called what? It is called Stokes equation, right? If you drop this turbulence terms also, this becomes another Reynolds equation. Then if you drop this viscosity, then if you consider only the gravity and the pressure and derive the equation for force and subsequently the acceleration, the flow equation that you get from here is conventional Euler's equation. And in that Euler's equation, if you keep the density as constant, you get your conventional Bernoulli's equation. Why I'm saying all this? Because you see, in this question, they have designed it in a very good way. Like, if you use a wrong concept, which as per you may be right because you're using Bernoulli's principle, and you will get the answer, which is option number C by Bernoulli, but then you have to be careful. Your conventional Bernoulli does not hold here because the density is changing. I will look at the whole problem, but first let me do the basics, Euler, and from Euler, isothermal and adiabatic equations, and then how do you use it in this question. So let us start. Okay, let us simply consider a pipe like this, some area, let us say dA, and let us call this particular length as ds, and let me call the height from here to here as dh, right? The liquid enters from here, the liquid leaves from here. Conventional Bernoulli जैसे derive करते हैं उसी तरह से कर रहा हूँ. So let me write all the forces first. The first force is pressure force. If I take the pressure here to be P, then in electromagnetic wave also, I had used this formula, that is, if something in electric field was changing, and then when I calculated the equation for E equal to BC and all that, I use this concept. So this is P. So here, if you have to write the pressure, and I tell you the rate of change of pressure with respect to S is given as dP by ds. So what will be the pressure here? The pressure here will be P plus dP by ds into the distance here, that is ds. Actually, it should be put as dou P by dou S because, see, the many variables, pressure is changing, time is changing, velocity is changing. If the things are changing, then you have to put a dou symbol. Okay, P plus this. And then the weight part. Weight is m into g. dm का mass लिखना है. How to be that? आप कहेंगे पहले volume लिख लीजिए. ds into dA. This is the volume part. ds into dA, length into area. Rho, this is the dm part, and then g. I take this angle to be theta. So I have to take the component of this weight in this direction. So that will be obviously ds, dA, rho, g, cos of theta. Now I do F equal to ma, very simple. I'm taking the direction of flow to be in this direction. So pressure is the P, and there it is that. So pressure is P minus P plus dP over ds into ds into dA. This is the pressure part. Okay. Then comes the gravity part in this direction, minus ds into dA into rho into g cosine of theta. This is equal to ma. M I have written here. इसको मैं copy कर लेता हूँ. ds dA volume into density into acceleration. Right? Okay. Now acceleration, you see, it will have a velocity dependent on time and velocity dependent on position. So what we are doing is we are considering only the positional change. So with respect to time, we are considering the velocity to be constant. That is, the flow is assumed to be steady. If it is steady flow, then dv by dt is equal to 0. But dv is changing with respect to s, so that part I will have to take care. So I'm writing this now. Okay, fine. You can see this p and p I can lose from here itself, and now I write the whole equation. ds dA, this will be rho v dv by ds. This term here will be equal to dp by ds dA. This term will be minus ds dA rho g cos theta. Cos theta can be written from here, from this triangle. I can take the cos theta that you can see is dh by ds. Okay, no problem. Now I can lose this ds dA, I can lose this ds dA and this ds dA. That is simple to see how. Now, if I just put it in the proper form and see what happens, this term should be like this. So p minus p, so this also will come with a negative sign. So I shift everything here and I get rho v dv by ds plus dp by ds, and then I get another term here, that is rho g dh by ds is equal to 0. So now if I arrange it and divide everything by rho, then what I can get? From here I will get v dv, from here I will get dp by rho, and from here I will get g dh. ds is gone, and this is equal to what? This is equal to 0. The integration of this gives you the conventional Euler's equation, that is v square by 2, simple. This is gh plus integral of change in pressure by density is equal to constant. This is the standard Euler. Now in this, we know that if this density is constant, if the density is constant, this dp will become p, and you will get your equation of Bernoulli, that is p plus rho, that is v square by 2, p by rho v square by 2, that is head equation, gh is equal to constant. And in your copies, you will find it as sum of pressure head, velocity head, and gravity head remains a constant, something like that. And then you have to bring this g down. So p by rho g v square by 2g plus h is a constant. So that is your conventional equation. In that case, this fellow rho is a constant. But in this question that they have given, rho is not a constant. It is changing. If the rho is changing, then we have to use this equation, not that equation. Okay? So now, how do we use this in different cases? So I will derive for you two standard cases. One is isothermal case and one is adiabatic case. In this question, they have used the adiabatic. So we will be using that equation directly and calculating our results. Fine. So all said and done, this is the equation. V square by 2 plus gh plus integral dp over rho is constant. Fine. Okay. So now I take first the case of isothermal case. Isothermal, what is the equation? Equation is PV is equal to constant. So I can say P by rho is some constant. Let us say K1. So I can calculate rho, that is P by K1. So if I use this here, so I will say dP, rho can be replaced as P by K1, and then you can write this as K1 into ln of P, and K1 itself is equal to P by rho. So P by rho ln P. The isothermal case, the equation becomes V square by 2 GH plus P by rho ln P is constant. This is your equation for what? This is your equation for your case of isothermal. And now if you're using it for adiabatic, then In adiabatic case, I can write that form P V to the power gamma. So P V to the power gamma is constant. Let us say K2. So I can replace this rho by this. So P by rho to the power of 1 by P by K2 to the power 1 by rho will be equal to this. I have taken here, this I have taken down. Now I will use this in this particular equation. So I will get what? You will get integral dp. Rho can be replaced from here. That is p to the power minus 1 by rho, p to the power minus 1 by rho, p to the power minus 1 by rho. And then this k2 to the power 1 by rho will come on the top, k2 to the power 1 by rho. Now this can be written as k2 to the power 1 by rho. This will be p minus 1 by gamma plus 1 and minus 1 by gamma plus 1. And then finally, this k2 can be replaced back from here. That is p into this k2 I am replacing. So if I replace this k2 here as p by rho gamma, so this will be p 1 by gamma, and then rho gamma will become rho, and this will be p minus 1 by gamma plus 1, and this will be minus 1 by gamma plus 1. Now you can see this term and this term I can lose, so I will be left with only p. So this is p by rho. Calcium le lete hain, so you will be getting gamma minus 1, and the gamma will come on the top. So what have you got? So we got the result for this here. So now in this case, your Bernoulli's equation becomes what? Your Euler's equation become what? It becomes v square by 2 plus gh plus p by rho, gamma minus 1 is equal to constant. This is in case of adiabatic. This is in case of isothermal, and this p by rho, that is the case of conventional Bernoulli's. Is that okay? Fine. So with this basics, now we are in a position that we can talk about the problem that they have asked. Two parts are pretty simple. You can easily get the answers to those. The third part requires this particular calculation. So let's go. Let me draw the figure here. Okay, fine. Ideal gas of density rho 0.2 kg per meter. So here the density is 0.2 kg per meter cube. Let me name it rho 1. Enters the chimney of height h. So this height is h. At the rate alpha is equal to 0.8 kg per second. So he has given you dm by dt. He has given you dm by dt. So let me write here. I think that is not coming on the board. So alpha is equal to 0.8 kg per second. This is dm by dt. Right? Fine. कितना रेट से एंटर कर रहा है, जितना मास अंदर एंटर करेगा पर यूनिट टाइम, उतना पर यूनिट टाइम लीव भी करेगा. A1 V1 rho 1 is equal to A2 V2 rho 2, and if rho 1 equal to rho 2, A1 V1 becomes equal to A2 V2. We know that. So now this is rho 1. What else is given? Area A1. Here the area is given as 0.1 meter square, and the area out here A2 is given as 0.4 meter square. The temperature of pressure and temperature here, 600 Pascal is the pressure at T1, and the temperature T1 is equal to 300 Kelvin. The temperature up here is 150. G is to be taken as 10 and gamma is to be taken as 2. So now we have to calculate what all the things. Pressure of the gas at the upper end, velocity of the gas at the lower end is 440, then upper end is what, height of the chimney is equal to what, and the density of the gas at the upper end is equal to what. So let us begin. First, let us calculate the density of the upper end. That is the simplest thing to do. Why? Because he has given you the alpha. Alpha here and alpha here is known to you. So I can start 0.8 is equal to A1. Area here is given to you as 0.1. So this is 0.1. Density here is given as 0.2. So this is 0.2 into A1, B1 into B1. So now you can clearly see 0.1 and this gone. 8 by 0.2. This V1 becomes equal to 40 meters per second. This is the velocity at this point. There also, if you want to calculate, you will require what? You will require the area, you will need the density, and you don't have the density for that particular reason. Fine. So let us go further. Process is adiabatic. So adiabatic, you have two equations. That is, one is PV to the power gamma, that is P rho to the power gamma is equal to a constant, and then you will have it in T form, that is T rho gamma minus 1 is equal to constant. So let us use them simply. First, let us, because temperatures are known at both the ends, we can use it. Temperature here is given to you as 300. Rho here is given to you as 0.2 and gamma minus 1. So this will be 1. Temperature there is given to you as 150, and that part, area here is not area, but the density that I have to calculate, root 2 to the power 1. So you can clearly see here, this and this I can lose. This is 2. So rho 2 will become equal to what? Rho 2 will be equal to 0.2. This and this gone. This will be 0.1. So you will be getting 0.1. So here you know the density to be 0.1. Okay, fine. Now, before we look at the answers, let us calculate the velocity also there. So 0.8 into A1 is 0.4. Then the density you have calculated, that is 0.1, and V2 you have to calculate. So 0.8 and 1 gone. This fellow and this fellow gone. 80 by 4, that is 20 meters per second. So here the velocity is 40. Here the velocity is 20. The density also is known to you now. The pressure part, the pressure at the lower end. The pressure at the lower end was given to you as 600. So this is 600. Rho is known to you at this end. Rho was known to you at this end. That is for the rho here, 0.2. So this is 0.2 square is equal to, then pressure at that end to be found out, P2, and then that end area, the density we calculated, 0.1, so 0.1 square. So you know the P2 now. P2 will be equal to what? P2 will be equal to 600 by 4, that is 150. Okay, so now let us look at the answers. The pressure of the gas at the upper end is 300. That is wrong, because the pressure at the upper end is 150. The velocity lower end is 40. That we calculated 40 and 20. So this answer is correct. The density of the gas at the upper end, that is 0.1. He has told 0.05, so that is wrong. A is wrong, B is correct, D is wrong. The main issue was the third part, that is the height of the chimney. He is telling you 590. Incidentally, if you use the conventional Bernoulli, you will get the equation as 590. So many people may say that is the right answer. But before you make the challenge, because the keys will be published, I think, on 1st of September. So at that time, 2 days from now, when you're challenging them that you are wrong, you're given this, please verify your facts and then challenge them. Right? So this here gamma is known to you, no? So if gamma is known to you, what I can do is I can simply put gamma here and write this equation in conventional form. So this is 2 minus 1 will be 2. So this becomes 2p by rho plus v square by 2 plus gh is equal to constant. So what I'll be doing now, this all I know, I'll just rub off, or I'll need these values, so I would rather keep them. 2p. First, let us talk about the lower end. So 2 into pressure. Pressure here is 600. So pressure here is 600. Rho here was known to us. The rho there was 0.2 plus v square 40. So this will be 800. GH, I'm taking the reference of this point, H is 0. So this is 0 equal to upper end 2. The pressure is 150. The density is 0.1 plus v square. V square was 20. So this is 400 by 2. That is 200 plus 10 into H. So now let us calculate. This and this gone, this 2 and 2 gone, this becomes 602 and 0.2 is 6,000. So 6,800, 6,800, and this becomes 0.1. So 3,200. So minus 3,200. So 0, 0, 6 and 3600 is equal to 10h. So h becomes equal to 360 meter. So the correct answer for the height of chimney will come out to be 360, not 590. Had you not taken this correction of gamma minus 1, you would have got your answer as 590, and then you would have marked it as wrong answer as correct, and you would have lost your marks. Okay, right. Let us move on to question number 12.